All right, our science class. Let's talk about weather patterns and severe storms. This is chapter 19. So air masses are really large bodies of air, 1,000 miles or more across, really big, and they kind of move across the ocean and land. And that's what causes our changes in weather. They're a few kilometers thick, and they have similar temperature and moisture levels at any given altitude. And then they move. Here's an image of global air masses, and they're given specific names because of their source region and also their temperature. So here's an example of a cold, dry air mass from Canada moving southward. And as it does, it slowly warms. Okay, so the same air mass, when it's at Winnipeg, the air temperature is negative 33 degrees Celsius. By the time it makes it to Houston, it's warmed up because Houston here receives more solar radiation. So the air surrounding, it's the same air mass and it's moving southward, but it'll warm up. But that'll bring a lot of frigid air that originates from Canada and moves southward. So air masses are classified based on their source region, and the source region is where the air mass acquires its properties, like whether it's humid or cold, or humid and warm, or cold and dry, or warm and dry. So for example, polar air masses, so imagine air masses sitting over environments like this. These are high latitude environments and they're typically cold. So the air masses that have source regions from here are very cold. Air masses that originate from the tropics, so imagine a place like this, they're low latitudes and they're typically warm, okay, because they receive more solar radiation. And then depending on where they originate or their source region, they can form over land. That would be continental, and that gets the sub-C letter. And so air masses that originate from continents tend to be drier, okay? And air masses that sit over the ocean, they tend to be humid air because of their ocean air interaction. And so there's four basic types of air masses. There's continental polar, so that would be this blue one over here. So it originates over a continent from polar latitudes. There's continental tropical, which would be this air mass here, an air mass that originates over a continent in lower latitudes. There's maritime polar, which is this one here and this one here in the Pacific and Atlantic. Originates over water, so that's why you get the maritime letter. And then polar because these are high latitudes, okay, 60 degrees north of the equator. And then there's maritime tropical, which are these in green. Okay, so this is lower latitudes and originate over the ocean. And you can have continental Arctic. I don't know if you've ever experienced one of those, what are they called? The winter vortex bombs. Those are continental Arctic air masses that move southward. So the air mass source regions in North America, they originate, so you have maritime polar here, like I showed you before, and in the Atlantic. Here's the continental polar, typically moves southward. This is the winter pattern. Okay, so in the wintertime, we have a lot of cold, dry air moving southward. That's where we get our cold fronts from. Occasionally we have maritime polar air kind of move southward. Out west, this is where they get a lot of their snowy weather when it comes to cool and humid air moving from west to east. Okay. Occasionally we get the continental Arctic air, very cold and very dry, moving south. All right, and then so what happens here, these essentially these different air masses battle out. They kind of move in and out of different regions and they push each other around. And then so the maritime tropical air masses that originate at lower latitudes, they will occasionally come in the wintertime and cover Florida, for example, and move into the south, right? And they originate from the lower Atlantic. In the summertime pattern, If you notice, Florida is just completely covered in the maritime tropical, and that's because this starts to dominate. In the northern hemisphere, it's our summer. We get more solar radiation, longer days. So these air masses start to move into the continent, bring a lot of heat and a lot of humidity, and that's why it rains almost every afternoon here in Florida. And they push back these air masses. So these are the typical patterns, summer and winter patterns for these air masses. So North America, they have a continental polar and maritime tropical air masses are the most important, especially east of the Rockies. So here's that maritime tropical air that can move in, and the maritime polar air, maritime tropical air east of the Rockies, and the continental polar air masses. These are the two air masses that are most influential in North America east of the Rockies. And the Rockies are like over here. So in this area, that's what drives a lot of the weather on the East Coast. So what we have, the continental polar, that's responsible for lake effect snows in the wintertime. What happens here, I don't know if you've ever been to like Western New York, like Buffalo, for example. The continental polar air mass moves across the Great Lakes and picks up a lot of moisture, and then that falls down as snow on the leeward shores of the lakes. Okay, and from northern Canada to the interior of Alaska, you get a lot of, in the wintertime, the continental polar air mass brings cold and dry air, and in the summer it will bring cool relief to those areas. Okay, and so here's that lake effect snow. So typically the prevailing winds blow in this direction, right? So this is where you see the maximum accumulation of snow. See on the leeward sides of the lakes, and so these areas will receive a lot of snow. Imagine having to be on a roof and having to shovel this stuff off. Yeah, I guess be thankful that sometimes be thankful that you live in Florida. Here in these dark blue areas, you can have over 130 inches or greater than 130 inches of snow. And that's, like I mentioned here, here's Buffalo. It's cool when they play football games. Their stadium is not a dome, so they'll play in that snow, which is fun. So here's that lake effect snow. Just moisture being picked up by these prevailing winds and then dumping it on the leeward sides of those lakes. East of the Colorado Rockies, we also have the maritime tropical air mass that dominates Florida. Okay, this comes from the tropics and moves in this direction, kind of can curve up into this direction. From the Gulf of Mexico and the Atlantic Ocean, it's warm, moist air that's unstable. Unstable means that it rises. It gets really hot, low density, so it rises. That brings a lot of rain to the eastern United States. We get a lot of rain in this region because of that tropical, humid, and warm air moving in this direction. Sometimes we can get it from the Gulf. And then there is, in the summertime, the formation of a continental tropical air mass that sits in southwest, the southwest, so Arizona, New Mexico, West Texas, and New Mexico itself, but it's hot and dry. And it's really small. So you can see it right here. Okay. So most of the U.S. or southern U.S. is dominated by maritime tropical air masses, either from the Pacific or Atlantic, but a small air mass forms here, very dry. So it's different from these moist, warm airs here. All right, and then there's the maritime polar air mass. This brings precipitation to the western mountains of the U.S. This is what I was talking about before. On the East Coast, that maritime polar is what creates those winter storms called nor'easters. And that's also not fun. This guy's using a snowblower to clear his, I think, driveway. But these are those low pressure systems that move in and dump a lot of snow in Massachusetts and areas of the Northeast. Okay, look at that. That's an approaching front. That's a boundary that separates different air masses. Remember, these air masses don't mix because they have different densities. So as an air mass is kind of moving through an area, like ominously through that where that Verizon store is, that is an air mass moving into a new area where there's an existing air mass. So air masses retain their identities. Warmer air is less dense, so what happens is that's forced aloft, meaning it's forced upwards. And cooler air is more dense, and so that acts as a wedge and kind of stays low. Okay. So a warm front is when you have warm air, like over here colored in orange, and it's moving in this direction, and it's replacing cold air. And over here, this blue area, this is cold air. Here's the location of the front. It's shown by a red line with red semicircles. And so what happens here is that it's kind of a slow moving front, okay? And so it moves and then it hits the cold air, and since the cold air is denser, it forces the warm air up, and as warm air is forced up, it's very humid. It starts to form clouds. That's where you see this here, okay? And so the front is moving in this direction. So warm air is going to eventually cover all of this area here. Like you could be here, this is your house, right? And so if you were looking outside your house, what you'll notice is that this slope here from the front, you see this kind of area here, this is a very shallow slope. So from your house, if you look up, you'll see really high clouds over here. And as the front approaches you, the clouds will become lower and lower because you'll be getting closer and closer to where the warm front is. So it has a slow rate of advance and also very light to moderate precipitation, and the precipitation lasts longer. So for example, if your house was over here, right? If your house is over here, you may start to have very light rain over here, and then it gets a little heavier as the warm front approaches you. Okay, so that's a warm front. Here's another image of it, a better image. I can't show you videos, so I've been really scouring the web for GIFs to show you. But here's the warm, unstable air being forced upwards. So here, this is the changing cloud cover. At first, if you're over here, you'll run into cirrus clouds, which are really high up in the air, then cirrostratus, then lower clouds, altostratus, and then the lowest clouds here, where most of the precipitation will occur, are the nimbostratus clouds. So you'd have moderate precipitation when a warm front comes through. Remember, those are typically, when it comes to us, those maritime tropical air masses. Now, cold fronts are a little different. Cold fronts are wilder. Okay, cold fronts are when cold air replaces warm air. And that's shown in this GIF here. This blue area here is a cold air mass. Remember, it's more dense than the warm air that's over here. So what happens is the warm air is forced upwards, and it's forced upwards really quickly. The slope of the front is much higher than a warm front, and cold fronts advance much faster than a warm front. So what this does, see how it forces all the warm air upwards, and then as you force warm and humid air up to higher altitudes, that cools down that air and causes water to condense to form clouds. And as that happens, the air is so humid, then you start getting heavy precipitation. So cold fronts are usually associated with intense precipitation. The duration is typically shorter. It's kind of like a passing fast shower, okay? And then the weather behind the front is dominated by a very cold air. It's air that's subsiding, meaning that it's coming from a higher altitude. It's like sinking air. And you get very clear conditions, a cloudless sky. Okay, so cold fronts are more violent. Cold fronts are typically when you would get some thunderstorms as well, and you can see that, I think, there, that's a thunderstorm. So we'll get thunderstorms occasionally, like tornadoes can form from cold fronts, especially in the springtime. So here it is. You get the formation of cumulonimbus clouds because you have very unstable air moving up very rapidly. And then that causes heavy precipitation, thunderstorms, but it passes fairly quickly. Okay, so that's a cold front. Then there's a stationary front. Stationary front, like in plate tectonics, is kind of like a transform plate boundary, where two air masses are just kind of going side by side in different directions, kind of like shearing past each other. So essentially, warm air moves in this direction and cold air moves in this direction, and this is the frontal boundary. So nothing really happens. Okay. Then there are occluded fronts. Occluded fronts are a little crazier. Occluded fronts are when a cold front overtakes a warm front, and you can see that in that GIF here. This is an active cold front, okay, and that active cold front is moving in this direction, right? But there's also a warm front right here, and it's also moving this direction. But the warm front is moving slower than the cold front, so the cold front catches up to the warm front. And as that happens, all the air in between the two fronts, which is warm air, gets pushed up really rapidly, and that cold air wedge pushes the warm air up and makes for some complex weather and heavy precipitation. As you can see at the end of the GIF, there's cumulonimbus clouds formation, thunderstorms, and heavy rain. Okay, so that's an occluded front. Here's again the progression. This is the warm air, warm front moving in this direction, cold front also moving in this direction. Cold front's faster, it pinches out all that warm air and forces it up, and then you get a lot of warm air going upwards, and that causes a lot of cloud formation, cumulonimbus clouds, heavy rain, thunderstorms, and then as the cold front kind of overtakes the other cold front, then you get light rain. Okay, let's talk about mid-latitude cyclones. These are huge low pressure systems that drive a lot of weather in the United States. They're the kind of primary weather producers at mid-latitudes. They typically, okay, so they move, here's the low pressure system. They rotate in a counterclockwise direction in the northern hemisphere. They move typically from the west towards the east. Okay, and so you can see they're made up of different air masses. Typically, it's usually the Continental Polar air mass as it kind of moves southward and turns in this direction. And then that interacts with the Maritime tropical air mass over here. And with the mid-latitude cyclone, what you'll have are a couple different fronts. You have a stationary front here, a cold front here. Cold fronts are indicated by a blue line with blue triangles, and then here's that warm front. And just imagine this rotation as a counterclockwise rotation. Okay, so the life cycle of a mid-latitude cyclone, they typically form along a front where air masses are moving parallel to the front, but in opposite directions. They include a continental polar air mass that's often north of the front, and the maritime tropical, which is south of the front. Okay, so here's that cold front advancing, and then the warm front moving in this direction. So the frontal surface kind of takes on a wave shape with a low pressure system at the center, and the flow is counterclockwise. The warm front and the cold front form, and they begin to rotate. And what happens is, because the cold front moves faster than the warm front, it catches up to that warm front and then creates that occluded front. And then that warm pocket of air is forced upwards, and that causes some crazy weather. Okay, here's another GIF of one here. This is a mid-latitude cyclone, and it's kind of slowly moving in this direction. See how all these clouds form? And that's because this is the cold air. See, this is the cold air that's moving in this direction. And that's a lot of times in the wintertime when we get a cold front that hits Florida. A lot of times it's from these mid-latitude cyclones, and the cold air kind of, the fronts kind of move into Florida like that. So you can see it forming there. These low pressure systems kind of take 2 to 4 days to pass over from western Midwest towards the east. And the larger weather contrasts occur in the spring. This creates the craziest weather, and that's because of the larger temperature differential between air masses. So the changing in weather as one of these low pressure system kind of moves, mid-latitude cyclones kind of move through, is at first you get a warm front. So you get clouds that become lower and thicker, you have light precipitation, and then after the passage of that warm front, the winds become more southerly and the temperature is warm. But then a cold front comes, and it's a wall of dark clouds. I had a GIF earlier of a kind of an approaching cold front. You get heavy precipitation. Sometimes you can get hail. Occasionally you can get tornadoes, especially if it's in the springtime. And then after the passage of the cold front, you get more northerly winds, clear skies, and a vast temperature drop. Okay, so here's one. Here's a low pressure system. Again, here's that cold front, remember it's moving in that direction. It's eventually going to catch up to this warm front. So imagine this whole thing kind of rotating, and that's how it's moving. At the same time, this is moving in that direction. So over here, this is where the cold front's actively taking over the warm front first, and then it kind of rolls over. Okay, so here in the northern part of the storm, or the low pressure system, you'll see warm air kind of pinched upwards, and the cold front has already overtaken the warm front. They've had their severe weather already, okay, and then all the warm air is kind of sitting on top of cold air, and a lot of cloud formation and a lot of precipitation. And then down here, this cross section from E to A, so that's E to A here, this is where active weather is occurring. So here's the cold front creating cumulonimbus clouds, heavy precipitation. Here's that warm front, and then eventually the cold air is going to overtake the warm air and then create this situation up here. So this is kind of like a cross section of each side of the mid-latitude cyclone. Okay, and then here's another satellite image for your viewing pleasure. So the air that is aloft is associated with cyclones and anticyclones. Cyclones are low pressure systems, and they have surface convergence. Okay. Cyclones and anticyclones are just high pressure systems, and they're generated by upper level airflow, and they're maintained by that airflow, and usually they're found next to each other. So whenever you find a low pressure system, okay, I don't have a slide for it, so if you have a low pressure system that's rotating in that direction, you'll typically find closer by a high pressure system with descending cool air, and they often occur together or close by to one another. You kind of move in similar directions as well. Okay, let's move on to thunderstorms. So thunderstorms typically form under cumulonimbus clouds. They're associated with heavy rainfall, lots of lightning, and occasionally hail. And if you live in Florida, we have a lot of thunderstorms here, and I'm sure you may have experienced some hail. In the world, there are 2,000 in progress at any one time, about 100,000 per year in the United States, and they're most frequent in, you know what, Florida and the eastern Gulf Coast region. So take a look at this map. This is the average number of days per year where there are thunderstorms. Remember, there are 365 days a year. So on average, those numbers mean that in this area, like over here, they get 40 days a year of thunderstorms. Check out Central Florida. We get 100 days of the year. Almost a third of our year, we get thunderstorms. And those 100 days essentially account for the summer season when we get afternoon thunderstorms every single day. So we get them a lot here. They do get them a lot here. This is associated with mid-latitude cyclones and the approaching cold fronts and occluded fronts. Okay, but we get a lot. This is where we get a lot of thunderstorms, and that's because of the incoming very warm and moist air. And in Central Florida in particular, we get sea breezes from either coast, west and east coast, and then they run into each other, and one of them's forced upwards, and that causes thunderstorms to form. And so all thunderstorms require warm, moist, and rising air. You can see that from this expanding cumulonimbus cloud. That is a lot of warm air that's rising and rising fairly quickly. And when that happens, you get a lot of moisture or water vapor condensing into liquid that releases a lot of heat, drives up and pushes air up faster. And then you get lightning and heavy precipitation as a result. They're most common in the afternoon and early evening. I'm sure you're very familiar with that. So they require continuous supply of warm and moist air. We've got a lot of that in Florida, and each surge of air causes the air to rise higher and higher. And then you get updrafts and downdrafts. Okay. Eventually, you'll have rain that forms. That's during the most active stage. You get gusty winds. You could have hail and lightning and a lot of heavy precipitation. Then after a thunderstorm kind of passes by, there's a cooling effect, and that marks really the end of the thunderstorm activity. Now, this is a situation that I'm sure you've experienced this as Floridians. Maybe you were on the beach when this happened, right? So typically a hot summer Florida day, what you'll have, because it's so hot, there's so much solar radiation striking the ocean and land, that causes a lot of warm air to rise. And then you start forming these large cumulonimbus clouds where you get a lot of unstable air rising. And as that happens, all that moisture starts to form water, which releases heat, or condenses to form more clouds. And that releases heat and drives up more motion. And I'm sure you've felt this. I'm sure you've been sitting at the beach and you see some cloud formation, and all of a sudden you feel like a very cold wind, right? You get this breeze of cold air, and then in your head you go, yeah, I'm from Florida, this has happened before. It's going to rain really hard in about 10 minutes. And that's what that is. So a lot of this warm air surges upwards, hits these upper areas of the atmosphere, it cools down, and then you get a downdraft. A lot of cool air will come down as this thing kind of moves in this direction. And so you'll feel this very cold downdraft. And that's when you start packing up your beach stuff, and you notice the tourists don't do anything. They're just like, oh, nice cool air. Then you're sitting in your cars, and then everyone else is getting drenched on, right? So you get heavy rain, perhaps some lightning. That happens pretty quick. Here's another gust front on the other side of the storm. Then afterwards, this is the light rain and the cooling effect. After the heavy precipitation has kind of gone through, then you get light rain and it gets much colder. Okay, tornadoes. These are local storms, smaller storms of short duration. They're essentially a violent windstorm, rotating column of air that extends from a cumulonimbus cloud, so similar to thunderstorms. But essentially they're a low pressure system inside and causes air to rush towards the tornado. And winds can hit 300 miles an hour. That's really fast and can be devastating. So those suction vortices can form inside tornadoes, which is pretty crazy. Here's one forming and kind of terrorizing as they move through. Okay, they're not very wide in diameter. Okay, so they're not very big, and on average they'll run for like 20 minutes. Okay, so they're short-lived. They're most frequent in April to June. All right, so in those kind of early summer, spring months, and they're associated with thunderstorms. The exact cause of tornadoes is not completely known. If not, we'd have a better way of predicting where exactly they'd occur. But this is our best explanation. It has to do with shearing of the wind. So we have weaker winds closer to the surface, and then stronger winds moving towards that rising aloft air in the cumulonimbus clouds. And because of the strong wind differential, the higher winds are moving faster than the weaker winds below. That causes this air to kind of spiral. And I don't know if you've seen tornado formation, but they kind of start off on their side like this, and then they point downwards, and then you have a full-blown rotating tornado here that makes like landfall. Sometimes they can be like up in the air before, and then they make landfall. And so they're at the bottom of these huge cumulonimbus clouds, and they basically suck air towards them, and then the air goes and spirals up into this rising cloud. All right, so tornadoes most often occur along cold fronts because, and in the spring months, because that's the highest temperature differential between the air masses from the continental polar air masses and the maritime tropical air masses. So that gives it the most energy. And they're associated with huge thunderstorms that we refer to as supercells, or just really large cumulonimbus clouds. Okay. So the characteristics, they're only between 150 and 600 meters in diameter, so they're not that large. And they'll speed across a landscape about 30 miles an hour. And they'll typically cut about 6 miles of a path. So a lot of tornadoes that form, a lot of times they don't do any damage because they'll be out on a farm or something and just, well, I mean, I'm sure the farmer's upset about it, like they'll lose crops and stuff like that. But as far as property damage, a lot of times tornadoes will just come down, touch down, and damage a landscape and not many buildings. Okay, and the maximum wind speeds have been recorded of 310 miles an hour. That's pretty devastating. Okay, here's the scale for tornadoes, EF0 to EF5. Okay, EF5 is ridiculous. All right, significant structural deformation to buildings. Let me just show you some pictures of damage. I'm sure you guys like that. This is the Hans Fujita scale. Here's the tornado occurrence. All right, in terms of time of the year, this is the peak of tornado season, right around April and May. All right, right there. So in the spring, and then it kind of dies down as we go into the winter months. And then here are the most tornado days, kind of peak just during spring, beginning summer. Now these are the areas that have the most tornadoes touch down. This is Tornado Alley right here. If you live in kind of north and west Texas, Oklahoma, Nebraska, this is where you get a lot of tornadoes kind of rip through this area. And again, remember those cold fronts from those low pressure mid-latitude cyclones that move in through this area will spurn off a lot of those tornadoes. But look at this, guys. A lot of tornadoes form in Central Florida, and the reason here is because we get a lot of thunderstorms. All right, the destruction of tornadoes can be devastating. If a tornado happens to go through a populated area, they'll rip the roofs off of homes. It really depends on how strong the tornado is, but if you're an EF5, most injuries and deaths occur because of flying debris. But fewer than 2% of tornadoes result in fatalities, and that's because they're so short-lived and so small. And it's difficult to forecast tornadoes because of that small size. Here's an example. This is a stop sign that was blown through a utility pole. Remember, this is like wood, right? And this is metal, and it basically pierced through that. So imagine being a human outside and having a stop sign just split right through you. Okay, here is a huge truck, which is kind of thrust upon this tree. Now, what's more incredible is that the tree has no leaves, and it looks like is stripped of its bark. How can you strip a tree of its bark? Yeah, very high winds. So the way we kind of warn people for tornadoes is meteorologists will issue tornado watches. They alert the public of the possibility of tornadoes within a given area. And that's only when the conditions are favorable. Like I said before, if it's a cold front, a lot of times tornado watches, they're about 65,000 square kilometers. And then you'll get an alert on your phone or your local news. Okay. Then they issue tornado warnings if one is sighted and reported or is indicated by weather radar. And the Doppler radar helps and increase the accuracy of detecting that motion. And so here, this is Doppler radar, and this would be the location of a hurricane. I'm sorry, tornado. Excuse me, tornado. Tomato. Okay. All right, let's see. The next slide was hurricanes. I knew that was going to happen. All right, you guys are familiar with hurricanes, from Florida. Hurricanes are when wind speeds exceed, or they're low pressure systems that form in the tropics, and they become hurricanes when these low pressure systems exceed 74 miles an hour. And it's a cyclonic circulation, counterclockwise, exactly like a mid-latitude cyclone. Okay, and so they form at low latitudes between 5 and 20 degrees north of the equator. So here's our kind of area of formation, right? They always talk about in the summertime, they talk about, oh, let's go look at the Atlantic Ocean basin and where those hurricanes form. And this is their typical tracks. Our hurricane season goes from August, or the most of them form in August and October. Our season goes from like, June 15th to like November 30th or something. Hurricanes also form out here in the Eastern Pacific, but we don't talk about them much because a lot of times they just go out into the middle of the ocean and don't really affect anybody. But we're not the only, we're not the only country and civilization that has to deal with hurricanes. In Australia, they've got their hurricane season is in the opposite of ours. They're in the southern hemisphere, so theirs is from January to March, and a lot of their hurricanes form in this direction and then hit this coast of Australia. Some form here, and these kind of circle around the Indian Ocean. Some can hit Madagascar. And then India is susceptible to typhoon formation, and also Southeast Asia from the Western Pacific. A lot of these typhoons kind of come in to this direction. So in the Western Pacific, oh, that didn't work out. In the Western Pacific, they're known as typhoons. Cyclones in the Indian Ocean, but they're all the same. It's the same storm, these low pressure systems. We call them hurricanes. And we may complain about having hurricanes in hurricane season every year, but the North Pacific actually, they get the greatest number per year. Let's talk about the parts of a hurricane. There's the eye wall. That's near the center of the hurricane. It's essentially, this is a plane flying through the eye and the eye wall. This here is the eye wall. Here in the eye wall, you have rising air and intense convective activity, and it's essentially a wall of cumulonimbus clouds. Let's see that again right there. That's that wall of clouds. And that is what generates the highest wind speeds right there closest to the eye wall, and that's where you have the heaviest rainfall. The eye itself is right here. That's what that plane flew through. That's how we collect a lot of data, we meaning NOAA. They send planes and they fly right through the center of the storm at really high altitudes. Still pretty dangerous, but they collect data like barometric pressure, wind speed, and stuff like that. And so the eye is at the center of the storm. A lot of times it can be 12 diameters or greater. There's no precipitation at the eye of the storm, and the winds actually subside. It was pretty crazy. I lived in South Florida when Katrina was a Category 1 and struck South Florida. And as a Category 1, wasn't a crazy storm, but still we got some pretty high winds. But then the eye passed. I was within the eye of the storm, and you could actually go outside during the eye of the storm, which is a bizarre thing because the sun is out, there's no wind, it's kind of warm, and you're like, whoa, what's going on here? Okay, and it's the warmest part of the storm. But the dangerous thing about that is that it's temporary, because as the hurricane continues to move, then you get hit by the other side of the eye wall. Okay, so here is a well-developed eye, and then this here is the eye wall. Okay, so here's a cross-section of a hurricane. In the northern hemisphere, they spin in a counterclockwise direction, and they basically pull air towards the hurricane, right? They pull this air and they force it upwards, and then the moist air kind of moves up. Any water vapor that has in it condenses, releases heat, and causes the air to rise even further. And that condensation leads to whipping winds throwing their water, and then that's where you have these kind of arms of the or rain bands of the hurricane kind of whipping water away from it. Okay, and then that air rises up to really high altitudes, and then there's sinking dry air right at the eye. Okay, here is time as hurricanes kind of passing through you. Here's the pressure at the eye of the storm. You'll have the lowest pressure right here. So this is the eye of the storm. And then here's the mean wind speed. And so as the storm approaches you, this right here has the highest wind speed. Okay, so here it's 60 knots. That's kind of the northeastern eye wall here. And then wind speed drops drastically in the center of the eye and then picks up, and this is the other side of the eye. One side of the storm, typically the northeastern quadrant in hurricanes in the northern hemisphere, have the highest wind speeds. Okay, and then the other side of the storm has pretty high wind speeds, but they're lower. So when a hurricane strikes you, there's a stronger portion of the storm. Okay, wind speeds can reach 300 kilometers an hour. And what can be really, you can see that from this damage here, what can be really damaging are the storm surges, okay? And you can see that here, flooding from the ocean. This is Hurricane Harvey when that moved over Houston. all this water came in, rushed in, and flooded a lot of the Houston area. So two major things is wind speed and flooding from the storm surge. Storm surge can be as high as 18 feet. So like the hurricane, you know, it's forcing air upwards. So it's like a vacuum cleaner. Imagine holding a vacuum cleaner over some water. That would pull the water upwards. Okay, and so as it's passing over the ocean, it's lifting that water up. And Category 5 hurricanes can raise the ocean level at most about 18 feet. So it's essentially like a big swell of water. And so as a hurricane kind of hits a coastline, it's going to flood the coastal areas. Okay, so hurricanes form in tropical waters, except in a few cases, eastern South Pacific and the South Atlantic. And the energy that powers a hurricane is from that condensing water vapor from those air masses that approach it. So once water vapor condenses into a liquid, it releases heat, and that heat drives more motion of the air. So they typically form in the late summer when ocean water is the warmest, and that provides the most energy for it to form. So here's sea surface temperatures, and sea surface temperatures are really warm in the late summer and along the tropical areas. Ocean circulation kind of pushes water in this direction, so a lot of tropical heat moves in this direction, and then this is where hurricanes form. They form here, and then they kind of follow these paths, and that's why we're kind of in their way. The initial stage of hurricane formation is not very well understood, but what will happen is a low pressure system will form, and that'll turn into a tropical depression. And a tropical depression are when you have wind speeds of 38 miles an hour. Then if this continues to strengthen, it becomes a tropical storm, and that ranges from 38 to 74 miles an hour sustained winds. And then we give it a name, right? I don't think there's ever been a hurricane, Sven. And then the intensity of the hurricane will increase if it moves over warmer water, because that's what gives it energy, that condensation and warm, humid air. But they'll diminish whenever they move over cooler ocean water, because that will decrease the amount of condensation and heat released. Or if they move onto land. If they move onto land, they kind of lose their fuel, okay? And so here, this is actually, this was Hurricane Harvey as it moved into Houston. And this is why it was so bad in Houston, because it came in, kind of hit this area of Texas, but then it stalled, and then it kind of moved down south, went back over the water, and then back north here. All the while, it was just raining a lot in this, in this whole area. Okay, and that's what caused a lot of flooding. All right, so here's an example, Hurricane Fran, the book uses. And it's approaching. You can see its pressure. If you have lower pressure, that's a more intense hurricane. And as it approached and hit North Carolina, kept moving northward, you can see the pressure decreased. Okay. I'm sorry, pressure increased. So decreasing intensity. And that's because it made landfall. All right, destruction from hurricanes. There's a lot of factors that affect what the destruction is. One is the strength of the storm. That's the most important factor. Higher category, 1, 2, 3, or 4, or 5. If you have a larger hurricane, more intense, that's going to bring more storm surge and higher wind speeds. Also, where it hits is very important. The size and the population density. If a hurricane strikes Panhandle, Florida, like Michael did, that was devastating for the communities that were there, but those are small communities. If you had, say, Hurricane Michael instead hit South Florida, Miami, or Fort Lauderdale, Homestead, those areas, a lot more people live down there, so it'll cause a lot more damage and maybe even loss of life. Also, the shape of the ocean bottom is very important, and the areas it hits. New Orleans, for example, is on a delta, a river delta, and it's not very high above sea level. So that's why when Katrina struck the Panhandle, or I'm sorry, Gulf Coast, U.S., that storm surge is what broke all the levees and caused flooding in New Orleans, which was absolutely devastating. And then we scale the hurricanes based on the Saffir-Simpson scale. I think nope, I don't have it there. But yeah, categories 1 through 5. This storm surge I talked about already. It's a large dome of water. It can be as wide as 40 to 50 miles. Remember that, 40 to 50 miles wide, and then at most, at a Category 5, 18 feet high. This is a picture of the aftermath of Hurricane Harvey and the flooding that occurred. Okay, yeah, so there's a reason why some of these houses are built on stilts, because this flooding is quite frequent. Look at that roof of this house. There's a lot of wind damage you can clearly see from some of the roofs on these houses, and a lot of inland flooding because of those torrential rains. Okay, and then this is beachside community. I think this is close to Galveston, Texas, when this hurricane kind of ripped through. And yeah, look at that, only a few homes still left standing in that flat kind of coastal area. So hurricanes can be really devastating. I'm sure you guys are very familiar, being from Central Florida. Maybe you guys have PTSD from like Hurricane Charlie or Irma. Irma was kind of bad.